All right, everybody, welcome back. So this is week 11 of the discussion hours, and today we will begin from where we left in the last week. And so we were looking into the radiation exchange involving real surfaces, and as I said in the previous week, we will look into a very important aspect of radiation heat transfer today, which is nothing but the view factor analysis, as you can see from your screen. And we will proceed from this. We'll proceed by understanding so basically you got a glimpse of this view factor analysis in the week's discussion, I mean, in the week's lecture series. But so primarily the idea is to solve some important problems involving this view factor analysis in radiation transfer. But before that, as we always do, I will present you a quick recap of what you saw in the week's lecture series, and then we will proceed with the problems involving view factor. Thereafter, as you can see, we will try to understand something which is known as black body radiation exchange, which will heavily involve the concept of view factor analysis, which we will see. And I don't think that we can cover radiation network today, but this is the subsequent discussion that will follow after the discussions of view factors and black body radiation exchange. We will primarily cover view factor today, and if there is time, we will look into this black body radiation exchange. As I said, this is a practical application involving view factors. For which we require the understanding of how to apply this knowledge of view factors into trying to understand radiation exchange involving black and real bodies, basically. All right, so let's get started. So as you can see from your screen, we will begin by giving you a quick recap of these view factors. So if so on your screen, you can see that there is an body of a given area AI, of which its differential area is denoted by this red or this orange region, whose differential area is given as DAI, having an unit normal NI, and the other body, which is body of area AJ, whose corresponding differential element is DAJ, and its unit normal is basically equal to NJ. Now, the centers of these differential areas are being joined by this line. The distance between this center to center distance of the areas DAI and DAJ is equal to R, and the unit normal makes angle theta I and theta j along the line joining the centers of these two differential bodies. Okay, so I believe we have seen the similar structure, at least this physical paradigm, when we are trying to understand the intensity of radiation. And trust me, the definition of view factor, which I will present now, actually comes from the definition of this intensity of radiation, by making an assumption there that whatever bodies we will be dealing with are diffuse bodies, and I will shortly clarify why do we basically use the assumption of diffuse bodies or diffuse surfaces when we define view vector. But nevertheless, so the view vector, which we generally call it as F, is defined as Fij, and this Fij reads the fraction of radiation, and this is how Fij is defined, which is nothing but the fraction of radiation leaving surface I that is intercepted by surface J. Okay, and this is the very definition of geometric view factors, or sometimes they are also called as shape factors. Okay, which says that out of all the radiation that leaves surface I, okay, what is the fraction that is intercepted by surface J is known as Fij, and this is called as the view factor of I, or basically this is known as the view factor, and we interpret as I said, the radiation leaving surface I interpreted by I mean intercepted by the surface J. And as I said, for a diffuse surface, or more precisely for diffuse emitters, I should say, and surfaces having uniform radiosity, you saw that Fij is mathematically defined, that is the view factor is mathematically defined as 1 upon Ai integral over the differential area, integral over the entire area of the differential element dai, integral over daj cos theta I cos theta j by pi r squared daj dai. This is the most fundamental mathematical description of the geometric view factor Fij, okay, which is nothing but, again I repeat, the fraction of radiation that leaves surface I, which is intercepted by surface J, okay, where you can see that in order to define Fij, or the view factor, Fij depends on certain things. First of all, it depends on the angle with on which the normal of the individual bodies basically make with the line joining the two centers of the two bodies. And when I say body, I now say the differential body, because we are applying this for a differential element and then integrating it over the entire area. Okay, so so Fij precisely depends on r square. It depends on theta I and theta j, which, as I said, is nothing but these angles, and r is nothing but the line joining the centers of the two differential bodies. Okay, so as I said, this very definition of view factor is general, except we are assuming the fact that the surfaces are diffuse emitters and they have uniform radiosity. Okay, the reason why we are assuming the surfaces to be diffuse emitter, because see, this very definition of this geometric view factor can be interpreted from the intensity of radiation, taking into account that the radiation that is leaving surface, for instance an eye, is independent of the direction which we are looking at, for which you can say that the intensity of radiation is basically equal to the emissive power divided by pi, and that is exactly from where this pi factor essentially comes. And that's the reason why I'll not show the derivation, but the derivation I believe is has been done uh, in the in the lecture videos of this week. But just to give you an idea that why this is why the surfaces are assumed to be diffuse emitter. That's the reason basically. Okay, because you are assuming that the intensity of radiation is nothing but the emissive power by pi. That's what you are basically imaging, and from there you are essentially, and from there doing certain simplification, you can form this definition of view factor, as you can see. Okay, so similarly, this Fij, as I said, is nothing but the fraction of radiation that leaves surface I, which is intercepted by surface J. You can also define something which is known as Fji, and now this is nothing but the opposite thing, that is the fraction of radiation leaving surface J, that is intercepted by surface I. And using the same analogy as we have written for Fij, Fji can now be defined as, so you can now define as Fji as 1 upon Aj integral over Ai integral over Aj cos theta I cos theta j by pi r square daj dai. Okay, let's say the second equation that I wrote. Okay, so what I wrote is similarly analogous to Fij, I can also define an equivalent Fji, which is now the fractional radiation leaving surface j that is intercepted by surface I, because as I said, in radiation you are always looking for the net exchange instead of the exchange taking place just in one direction. Because as we saw, radiation is typically multi-directional in nature. So we can also equivalently define an Fji, which is nothing but the fraction of radiation leaving surface j, which is intercepted by surface I, and analogous to equation 1, it takes the following form, as you can see. Now, more importantly, you can see that the integrand, which is this factor, cos theta I cos theta j divided by pi r square, is same in equation 1 and equation 2. So, you can now infer that since the integrand of 1 and 2 are same, you can then infer that Fij times Ai is basically equal to Fji times Aj. Okay, and that's a simple relation that you get typically because since this integrand is just the same, you can bring this Aj into the left hand side, and similarly you can bring this Ai into the left hand side of equation 1, and then since this term is just the same, from 1 and 2 you can infer that Fij times Ai is equal to Fji times Aj. Physically you can think of it like the fraction of radiation leaving surface I, that is intercepted by surface j, multiplied by the area of surface I, is equivalent to the fraction of radiation leaving surface j, which is intercepted by surface I, multiplied by the area of aj, precisely. Okay, and this relation is so popular that it has got a name. This is known as the view factor reciprocity relation. Okay, so that's one of the important relations that you will need in order to solve numericals associated with view factor, and typically it is known as the view factor reciprocity relation, which has got this following form. Maybe we can call it some equation 3. Okay, I hope things are clear up to this point. Now, similarly, there is one more relation involving this view factor, is the fact that suppose you are considering, let's say, a surface, any generic surface, let's say I, this I can be curved, this can be flat, maybe I'll draw a curved surface just to generalize thing. So where I is any curved surface. So for the radiation that is being emitted by this surface I in all possible direction, again considering the fact that I is a diffuse emitter, the radiation that is leaving surface I, you can form a fictitious number of, let's say, surfaces, uh, and these surfaces basically starts from 1 2, and this goes up to the nth surface. Okay, meaning that what you are now trying to do is that you are considering a surface I, which is of course diffuse, which is emitting radiation in all possible direction by as the word diffuse emission means. Now, in order to capture this radiation coming from surface I, you are forming a fictitious number of, fictitious means they are actually not real surfaces, but you are forming a number of, let's say, n surfaces which will capture all the possible radiation that is basically coming from this individual surface I. Then if you just apply a simple concept of energy balance, you can show that Fi1, which is again nothing but from the very definition of view factor, it is just the fractional radiation leaving surface I, which is intercepted by surface 1, plus Fi2, again, which is nothing but the fraction of radiation leaving surface I, which is intercepted by surface 2. And remember, this I can emit in all possible direction. Okay, just don't go by the direction of the arrow. It is just a generalized surface that I am considering. So which means that I can now write this for up to the nth surface, which is, let's say, up to fin, and this should be essentially equal to 1, because remember, the sum of all the fractions has to, go to unity, because that's what that I mean that's how, these fractions are essentially defined. Which means if you now consider a surface, let's say I, the sum of all the possible view factors that can arise from I, that basically goes to unity. And this, in shorthand form, this is basically, so in shorthand, this summation can be written as, let's say, summation j going from 1 to n, fij is basically is equal to 1 for any generic, for any generic ith surface. Okay, and this relation has also got a special name, uh, and this relation is known as the summation rule for view factors. Okay, so now you have at least two important relations that we saw. One, the view factor reciprocity relation, which is nothing but the fij times ai is equal to fji times aj, and the view factor summation rule, which says that for any generic ith surface, the sum of all the view factors basically, goes to unity. Okay, I hope you are clear up to this point. Okay, all right. So so that's it. So this is just a basic introduction to view factor and the two important relations involving view factor. And now, straightforward, we will start off with some basic numericals involving this view factor analysis, and taking into consideration. So we will basically require three things. One, the definition of view factor, the most, I would say, the most general definition of view factor, which is given by equation 1 or by equation 2, the view factor reciprocity relation, and the view factor summation rule. With this, just from these three important, relations, I would say, I mean, you can do any, I mean, you can, attempt any numericals involving view factors at your end, and a few glimpses of these numericals I will show in this today, in this discussion hour. Okay, and the first numerical, as you can see from your screen, is something like this. You can have a look at this numerical. Maybe I'll stop here for a couple of minutes such that you can read out what is basically asked in this question, and then I'll formally show you how to approach this problem. Okay. So as you can see from your screen, let's read the question once. So it says that consider a diffuse circular disk of diameter d. So this is the disk. Remember, it's a disk of diameter d, and its area is given as aj, and a plane diffuse surface of ai, which is this. So ai is much less than aj, is what they have said. The surfaces are parallel, meaning that the line joining the centers is basically along this, which also means that the unit normal of these two surfaces are equal, and they are basically collinear. That is something that you can interpret. And then they are saying that the surfaces are parallel, and ai is located at a distance l from the center of aj. meaning that this surface is located at a distance L from the center of AJ. And then given all this information, they are asking us to obtain an expression for the view vector Fij. So we just require to find this Fij, and as I said, in order to utilize the expressions of view factors that we just saw, we will have to consider an important assumption, which is the very fact that this uh, surfaces AI and AJ, these are diffuse surfaces, and as given in the question, AI is significantly less than AJ. Okay, and of course we are assuming uniform radiosity from the surface AI. Okay, so given this, we are asked to find out the view factor Fij. And remember, we will just utilize three things in order to solve any problem involving view factor. The first is the generic definition, mathematical definition of view factor, and if required, the view factor reciprocity relation and the view factor summation rule. Okay, so I mean, as we can see in this problem, the things that we will require here is the fundamental definition of view factor, which is, and we will start off from there, that is from the definition of Fij, which is the fraction of radiation that basically leaves surface I, which is intercepted by this surface J, is given as Fij is equal to 1 upon Ai integral over Ai integral over Aj cos theta I cos theta j divided by pi r square, where we will define what r is in this, or it's basically given, and we will see what r is in this scenario, and it is integrated over daj dai. Okay, where r is nothing but, you pick, see, this is a finite body, this is not a differential body. Okay, which means that in order to use this generic definition of view factor, you need to pick an elemental area in this finite, you need to pick an elemental area out of the total area involved in this body AJ, which is given by the shaded region, as you can see. And maybe I'll also draw some shades here such that it becomes clear to you. And r is nothing but the distance between the, I mean, if you, so r is nothing but, if you pick an elemental area here, okay, let's say this particular area, then r is nothing but, and maybe we'll call this elemental area as daj. And as we saw from the definition of view vector, r is nothing but the distance joining the center of this daj to to dai precisely. And if you, I mean, in order to make things more clear, maybe I'll draw the picture here once again. So basically we have this dai, which is a differential area, but we also have a disk. So we also have a disk. But remember, now the area of this disk is not differential, it's a finite, it's a disk of finite, oops. So maybe it's a disk of finite, it's not coming. Maybe I should draw it something like this. Oops. Maybe I'm just very bad at drawing. That's what it says. Okay. So yeah, maybe something like this. Please excuse my drawing. Anyway. So so now maybe this is the disk of area AJ, and we are defining a differential area. So remember, this is the disk. So this is precisely a hollow surface, something like this, where this distance, which is the line joining the center of the entire area AJ to the differential area AI, is given as L. But we also now need to define a differential area which is at a particular, let's say, R of the radius of the disk, having a thickness dr, and our elemental area is precisely this area. So if I kind of zoom out, or in fact, if I zoom in this picture, you will precisely see that so what I'm doing is I'm just zooming this particular picture. So what you will see, that you will basically see a elemental area DAJ, and this particular differential area DAI, and precisely R, and precisely as I said, R is the line joining the center of this DAJ to this DAI. And I hope this is clear to what I am saying. But remember, it is not that R that is given in the problem, it is this length L that is given. But remember, this R is now located at any generic generic radius R, which means that my DAJ, first of all, I can infer from this exercise that my DAJ is nothing but 2 pi r dr. Okay, that is something that you can infer. The second thing, so what you can say is that since the line joining, since the unit normals of surfaces AI and AJ are in the same direction, since this is NI and this is NJ, and since so I'll write it down, since NI and NJ are collinear, this implies straight away from the geometry that cos theta I will be equal to cos theta j, and we'll call it as cos theta. But remember, cos theta I and cos theta j is the angle, okay, which the normals of the individual surfaces make in with the line joining the center of the two surfaces. Precisely what cos theta will mean here is that this is basically the theta that I am considering. That is typically because the unit normal of this surface so this you can interpret that the unit normal of this surface will face in this direction, which is nj, and the unit normal of this surface is precisely in this direction, which is ni. That means the angle, okay, with which the unit normal of surface I make with the line joining the centers of the elemental areas dA and dAj is equal. As you can see, that is typically equal because this angle will also become equal to theta. Okay, I hope you can understand, and that's the reason why precisely this is theta j and this is theta I, and just from geometry you can say that this theta I is just equal to theta j because these unit normals are basically facing in the same direction, and that's one of the most important aspect in this problem in order to proceed with calculating this view factor Fij. Okay, so that's something that I have wrote here, and that's something that you can infer geometrically from this figure. And remember, what I am drawing here is basically the zoom. So I'll write it down. This is the zoomed in vision of whatever is happening out here. Okay. So since theta I is equal to theta j, you can infer from this definition of Fij that this Fij is equal to 1 upon Ai integral over Ai integral over Aj. This now becomes cos square theta j by pi r squared dAi dAj dAj. I hope you are clear with me until this point. Okay, all right. So now we'll do one more simplification. So since this surface AI is a differential surface, what I can do is I can write this as 1 upon AI integral over AI dAi integral over Aj cos square theta pi r square dAj. The reason why I can do is because this dAi, which is the, which is basically, which is the area which is emitting radiation, this area, so typically this is a differential area, which means that Ai is much less than Aj. That's what they have said, meaning that this is a differential area that we can consider with respect to the area of this entire disk precisely. So then this integral simply turn out to be 1 upon Ai times Ai, because this integral will just give you Ai, and then this, we just need to evaluate this integral, which is integral over the surface of Aj cos square theta by pi r square dAj, which means Ai and Ai will cancel, and my expression of Fij further simplifies to integral over Aj cos square theta by pi r square dAj. Okay, now we need to understand certain things. So what we need to do is, this r is not given to us. Instead, what we are given is, we are given this length L, which is the line joining the centers of the differential area to the center of the disk. Okay, so from geometry I can infer, so from this geometry, okay, from this very particular geometry, I can infer that my cos theta is typically equal to L by R, and since R is not given, I can write this R as so this R can be written as L square plus R square. Okay, where this R is precisely the radius up to which we are considering the differential area. Okay, so then I can write this particular integral, as you can see, as, so how can we write? So I can write this as Fij times integral over Aj. Cos square theta basically becomes what? So cos square theta will become L square by L square plus R square whole square times 1 upon, so this is 1 by pi R square, and similarly I can write my R square as, so did I do any mistake here? Okay, sorry. So I did, so actually this R, so I think I did a mistake. So R is actually this, so it's a root over of this typically. That's just from the geometry. And R square is actually L square plus R square. Okay, which means cos square theta will just becomes L square plus R square. Sorry for an error in the math. So 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 this is just geometry, right? I'll just show it again. So we had this particular L, we are picking a generic R, and this was typically my capital R, and this was theta. So your cosine of theta will just be equal to L by R, and from the theorem of Pythagoras you can write that R is basically equal to L square plus R square to the power half. Okay, that's what, so typically that's what we are kind of doing here. I hope it's clear. It's just the Pythagoras theorem that we're applying. Anyways, so then this is just L square plus R square, and then we have this pi R square term here, and this R square is typically again L square plus R square. Okay, and then this is dAj, and remember we have evaluated dAj as 2 pi R dr. So now things are a little bit clear. So this pi and pi would cancel. So your Fij precisely turn out to be what? So it is integral over, so now since this integral you are writing in terms of dr, so you need to integrate it from 0 to r, which is nothing but the diameter, which is d by 2 basically. Half the diameter, which is d by 2. So you are integrating this, and this is L squared by L squared plus R squared. In fact, it is 2L squared by L squared plus R squared whole square. Okay, and then there is this R dr which you need to do. So that's it, guys. We just simply need to evaluate this integral in order to define the view factor. More importantly, this L square is not a function of small r, so this will come outside the integral, which means this can be written as Fij equal to 2L squared times integral 0 to d by 2 r dr by L squared plus r squared whole squared. Okay, so you can, so if you do this integration, you can make some substitution to do this integration. You can try it at your end. I have already done this. So this integration, when simplified, leads to the fact that your view factor Fij simply turn out to be d square by d square plus 4L squared. Okay, so that's what you can do. So that's the expression of view factor in terms of the diameter of the disk and the line joining the centers of the two disks. Okay. So I hope this is clear, and I hope this particular math is clear, where we have, used the fact that the unit normals basically face in the same direction, which means that theta I and theta j are just equal. Okay, that's what we have written. And then we have expressed this cos theta in terms of this capital R, L, and small r, and basically we tried to eliminate this capital R from this, because we require our answer in terms of L and then integrating it over the radius of the disk, for which we require this small r typically. Okay. Okay, I hope this is clear. I'll stop here again for a couple of minutes, and then we'll proceed with the other important numerics. In the meantime, I will just go and bring a cup of hot water. I'll be back in 1 or 2 minutes. Okay, so this is one such example where we have utilized the generic definition of view factor into calculating the quantity Fij, and now we'll look into a different set of numerical, where we will see that we will use the other two aspects, which is the reciprocity relation and the summation rule, into calculating the view factor. Okay, so typically in the question, as you can see, we were asked to find the view factors f12 and f21 for the three given sets of geometries. In the first case, it's given that there is a sphere of diameter d inside a cubical box of L equal to d, where the length of this cubical box is equal to the diameter, is what they have said. And in this given scenario, we require to find the view factor, which is f12. So f12 is the fraction of radiation leaving surface 1, which is the surface of the sphere that is intercepted by the cubical box, and the other way around, which is f21, basically. So let's do this. So let's try to solve problem 1. So, so what we require is to find this f12 and f21, and let's see what we can infer. So, first of all, you can see that since this sphere is completely enclosed inside this cube, okay, so if I write the summation rule, so if I write the summation rule for 1, which is the sphere, I can write that f11 plus f12 is basically equal to 1. Okay, but this f11 is not known to us, right? We don't know what is f11. But if we carefully see into the picture, we can actually get f11 because sorry, because let's try to see what is f11. F11 is nothing but the fraction of radiation that leaves the sphere surface, which is intercepted by the sphere alone. Now that typically for this scenario is precisely 0, right? Why? Because any radiation that will leave a spherical surface will never intersect the surface onto it precisely, because they kind of travel in straight lines. Okay, so it cannot happen that unless and until it leaves the surface from all possible direction, it cannot come back and enter the surface and strike the surface. uh at least if you don't put reflectors on it. But again, if you put reflectors, that's the radiation which will come from the reflector precisely. Okay, so which means it is not possible for f11 to be a non-zero quantity, because from this very figure, the radiations which leave this spherical surface, it will basically go into all possible direction as I have indicated in this figure, and it will never strike on the surface alone, which means this f11 equal to 0, and this we have obtained by inspection precisely, which means one of our unknowns, which is f12, now basically becomes equal to 1. That's the answer to one of our part. Now, in order to find f21, we will be using the reciprocity rule, which we have learned, which is f12 times a1 is equal to f21 times a2. Sorry, this is uh, this is f21 times a2, and then f21 can be written as f12 times a1 by a2, and we just require to calculate this a1 and a2 in order to determine f21, because f12 is already known. So my a1 is nothing but, so f12 is just 1, a1 is nothing but the the surface area of this sphere, okay, of diameter d. So this becomes pi d square um, in terms of its diameter d, and a2 is the surface area of the cube, which is nothing but 6l squared. But we know that d is precisely equal to l, which means this f21, which is the fraction of radiation leaving the cube that strikes the sphere, is nothing but pi by 6. That's it. So you can now interpret that while all the radiation that leaves the sphere strikes the cube, but it's not the other way around. That is, only this much fraction of the radiation that leaves the cube precisely strikes the sphere, which means that if I although it's not asked in the question, if I apply the summation rule for 2, I can say that F22 plus F21 is equal to 1, which means that my F22, which is the fraction of radiation leaving the cubic enclosure, is equal to 1 minus pi by 6, which is equal to 5 pi by 6. Which means that out of all the radiation that leaves this cubical enclosure, pi by 6th fraction of it will be intercepted by the sphere, and 5 pi by 6 will be absorbed from its own walls typically. And that makes sense, right? Because if I draw this picture in a larger sense, I think things will be clear. Maybe I'll draw it something this like this. Okay, so now at least you can interpret that from the sphere, whatever the radiation that will leave will strike the cube, and that's the reason why F12 is typically equal to 1. But from the cuboid, a fraction of it will strike its own walls, and a fraction of it will strike the sphere, where this 2 is the cube and 1 is the sphere. And that's the reason why we get this F22 to be 5 pi by 6, and F12 is typically 5 by 6. I hope now these aspect of view factor is also clear to you, that how do we apply the reciprocity relation and the view factor summation rule. Let's do the second example and things will be more clear, where in the second example, if you go into the problem, you can see that we have one surface which is 1, we have another surface 2, and we have the third surface which is 3. And so this is basically one side of a diagonal partition within a long square duct. So basically it's a duct where you are getting the, I mean, the cross-sectional view. So this duct is typically something like this. And there is this partition that is taking place inside this duct. And in this context, we require to find what is the fraction leaving this partition wall that strikes this surface 2, and what is this F21 in this context. Okay, so let's try to do problem 2 now. So let's draw the picture. This is a square duct with a partition where this partition is named as 1, this surface is named as 2, and this is named as 3, and we need to evaluate what is F12 and F21. So the same principle that will apply, that first we'll apply the summation rule for 1, which is the partition. And if you apply the summation rule, you can see that my F11 plus F12 plus F13 is basically equal to 1. Okay, that's the view factor summation rule that I have applied, which is just this summation of j equal to 1 to n. Fij is 1, and here in this case j is basically equal in this case your n is typically equal to 3. That's what we have applied. Okay, now since this is a square duct, as you can see, this means you can use the principle of symmetry to interpret that whatever the radiation that leaves this partition wall will be equally divided, and will be equally intercepted by 2 and 3. And that's the symmetry argument that we are saying, because by symmetry, so what I'm saying is, in fact what I'm arguing is, by symmetry F12 will be equal to F13. Okay, that's one thing. And because this is a plane partition, f11 is nothing but the fraction of radiation leaving 1 that will be intercepted by 1 is simply going to be equal to 0. Okay, which means this is 0 and f12 is equal to f13, which means I can write that 2 times of f12 is typically equal to 1, which means f12 basically becomes equal to 0.5. Okay, all right. And then if f12 is 0.5, I can now use the view. So I can use the view factor reciprocity relation, which states that a1 f12 is equal to a2 f21, and my f21 typically comes out to be a1 by a2 times f12, where if I consider this length as L, this basically becomes root 2 times L, and since the width, so you can consider your width to be unity, so width is taken to be equal to 1, which means that my a1 will simply be equal to 2 times of, so root 2 L times B, which is 1, so we can discard this B, and this is just L, and f12 is equal to 0.5, which means my f21 typically is equal to root 2 times of 0.5, and if you do this, you'll get it to be around 0.71. So your f21 is equal to 0.71. Okay, so this gives you the f21 in this scenario. I hope this is clear at your end. And thus, in the similar spirit, you can also calculate the f12 and f21 for the scenario, and I'll just leave you this exercise as a homework. You can try it at your end, and if there are any doubts, you can let me know through the discussion forum of the course. Okay, and anyway, so you can try it at your end. Think about it. How will you basically calculate this? Where the third case is a cylindrical tube of equal length and diameter, and you basically need to find out the f12 and f21 in this scenario. Okay, so that's a homework that you can try at your end, and I'll discuss this in the next class in any way. So the point what I wish to make in the make now is that if you pay a little bit closer look into the examples that we did, for instance, this example and this example, you can see that while we were trying to calculate the view factors, some of the view factors were obtained from the summation rule and the reciprocity relation, while some view factors were needed to be known a priori. Either you can evaluate them by inspection, or making something, or making some symmetry arguments, but at least you need to know that view factors a priori in order to completely determine uh, the in order to completely determine all the view factors. For instance, just in order, I mean, just to give you an example, if you have two surfaces, so this is a note which I want to say. So let's say for two surfaces, say 1 and 2, you can now infer that there is going to be 4 view factors. So the total number of view factors that can arise is going to be 4, because you can have f11, you can have f12, you can have f21, and you can have f22. Okay, so this is nothing but all the possible view factors involving 1 and 2. Okay, Now, out of these four view factors, okay, you can say that from the summation, so you can say that, from summation rule, so if you apply the summation rule for one, you will basically, get one view factor. And if you apply the summation rule for two, you will basically get, another view factor, which means two view factors you can obtain from, so two view factors can be obtained from the summation rule. Okay. And one view factor can be obtained from the reciprocity relation. I mean, that is something that we have seen through these examples, which means for a surface 1 and 2, out of all the possible view factors, 3 can be obtained from the summation rule and the view factor reciprocity relation, but there is one view factor, which needs to be known. And that's typically what we have done in the first example. Remember, we said that this F11 is typically equal to 0 by inspection. Because F11 is 0 by inspection, all the other possible view factors can now be completely determined, because remember, three view factors can be known out of four from the summation rule and the reciprocity relation, because we'll have two summation rule for two surfaces and one reciprocity relation, which means for two surfaces which will generate four view factors, three will be obtained from equations and one you have to obtain that either by inspection or it has to be given to you a priori. Similarly, you can now generalize this for n number of surfaces, and that's the motivation for the next problem that we will try to figure out. Okay, so just how we witness it for two surfaces, what the next question asks you is, if you now have an enclosure of n surfaces, how many view factors needs to be directly determined, which means that how many view factor you need to know a priori in order to determine the complete set of view factors in for an n surfaces or an n enclosed surfaces precisely. For instance, if you have a hexagon of this form, which is kind of an enclosure, how many view factors needs to be determined directly, and we are kind of generalizing this aspect to an n surface enclosures typically. So these kind of configurations are known as n surface enclosure. So I hope you understood that the question what I am now asking is that I'm trying to generalize the concept of a uh, two body thing or a two body enclosure to an n body enclosure, where I'm now asking that how many view factors you precisely need to know directly in order to determine the complete set of view factors. And this and this is something that we will try to address in this problem. Okay, so at least now you can interpret that if there are n surfaces, the total number of possible view factors that it can generate is going to be n squared. So if there are n surfaces, the total number of possible view factor is going to be equal to n squared. And precisely I will prove you why this is going to be equal to n squared. So in order to do this proof that the total number of possible view factor is going to be n squared, first of all you can pick a simple case where there are two surfaces. So we saw that for surfaces 1 and 2, there are four view factors that are possible, which is f11, f12, f21, and f22. Precisely that's what we saw in the examples in this example that I discussed. So for two surfaces, there are four view vectors. So you can generalize this for n surface, which will have n squared total number of possible view factor, and I'll basically prove you that there will exist that the total number of possible view factor that can exist is going to be n squared. And in order to show you this proof, I will precisely form a matrix which is known as a view factor matrix. So from this view factor matrix, I will show you that the total number of view factors that will be possible is going to be equal to n square. So let's see how I can form this matrix. So if I can pick, let's say one surface, let's say I pick this one surface and I apply the summation rule, I can say that, or it's not the summation rule. So if I just pick a generic, let's say one surface, the total number of possible view vectors that can arise from this surface 1 is going to be what? So it is going to be f11, it is going to be f12, it is going to be f13, and I can continue this up to f1n. So just from this one surface, I can get this n view factor in this, and I have arranged this in this column wise. Similarly, if I now pick, the second surface, let's say this surface, the total number of possible view factors that can form, or I can form, is going to be f. So this is precisely going to be f21, f22, f23, and this is also going to extend up to f2n. And I can, sorry, and I can extend this for the third surface as well, which is going to be f31, f32, f33, and this will continue up to f3n. And if I do this exercise, I can write this up to nth surface, which is going to be fn1, fn2, fn3, and this will continue up to fnn. Okay, so so this big matrix that I have drawn consists of all the possible view vector that can arise from the n surfaces that typically form the enclosure. Okay, so you can see that in this matrix there are n columns and there are precisely n rows. Okay, so because this matrix so basically this matrix consists of n columns and n rows, so the total number of elements in the matrix is just going to be n cross n, which is nothing but n square, which is nothing but the total elements in the view factor matrix. Okay, so precisely, let's take the example of a two surface enclosure. I mean, you cannot form an enclosure with two surfaces, but let's take the example of any two surfaces. So your view factor matrix in that will be just f11, f12, f21, f22. So this is the view factor matrix. So this is your VF matrix for two surfaces. Where you can still form an enclosure because you can anyway pick a generic surface 1 and then say that your surrounding is your second surface basically. So everything else you can call it as a second surface, and then you can say that this is the view factor matrix that will arise from these two surfaces. So now you can interpret that the number of elements in the view factor matrix is nothing but all the possible view factors that can arise. So in this view factor matrix, you can now say that you can apply the summation rule for the first surface, and then you can say that this is the sum of this is basically going to be equal to 1, which means from the first surface you basically get one summation rule. And if you extend this for all the n surface, you will precisely get n summation rule. So out of the total n square view factors, n view factors can be determined from n summation rule. And that's obvious, right? Because for each surface or for each row, you can have one summation rule. Okay, because like f11 plus f12 plus f13 up to f1n, this is equal to 1. You can similarly have the sum of all these things to be 1 and so on and so forth. Which means, and similarly, for let's say two surface, you can have basically two summation rule. So sum of this is 1, sum of this is 1. So which means that from the summation rule, because from the summation rule you can determine n unknowns, so you can determine n unknown view factor from n summation rule, and in the same spirit you can show that n into n minus 1 by 2 view factors can be determined from the reciprocity relation. Okay, which means that the possible view factors that can be completely determined are n plus n into n minus 1 by 2. N comes from the n summation rules and n into n minus 2 comes from the reciprocity relation when we apply it for the n surfaces, which now draws the conclusion that out of the total possible n square view factor minus the view factor that you can obtain directly, which is going to be n plus n into n minus 1 by 2, the subtraction of this from this will give you the number of view factors that you need to know a priori, or it should be directly given to you, and if you do this subtraction, this will just come out to be equal to n into n minus 1 by 2. So typically you need to know this n into n minus 1 by 2 number of view factors directly. So this is the number of view factors that needs to be known a priori or beforehand, or something by inspection or by symmetry or things like that. You can draw this similar analogy for a two body enclosure. So for instance, if n becomes equal to 2, n into n minus 1 by 2 just comes out to be equal to 1, which means that one view factor you need to have, you need to precisely know directly, and that's typically what we did when we solve this first example, where I have said that f11 is typically equal to 0 by inspection. So either you need to know it directly or you need to know by something else, but at least one view factor out of the entire four view factor needs to be known directly for a two body enclosure. Typically, in the same spirit, n into n minus 1 by 2 view factor out of the possible n square view factors needs to be known a priori if in order to determine the entire view factor for an n zone enclosure. Okay. If you do the similar analogy, if you pick n to be equal to 3, which means n square is going to be equal to 9, which means that the view factor matrix is going to be f11, f12, f13, f21, f22, f23, f31, f32, f33. So this is the view factor matrix for the case when we have three surfaces, and then n into n minus 1 by 2 is going to give you what? So it is 3 into 2 by 2, which means, so which means three view factors needs to be determined. So this, which means three view factors needs to be known directly. And that's obvious, right? Because if n is equal to 3, you will precisely have 3 summation rule. And you will precisely have 3 reciprocity relation. Which means 6 view factors are obtained out of 9, and which means you need 3 view factors which you precisely need to know directly. And typically you can verify this from this exercise that we did here. Okay, I said that f11 equal to 0 from from the fact that that's by inspection, because no radiation from 1 can strike 1 itself. And I say that f12 and f13, either of these two is obtained from the symmetry argument. And similarly, one more view factor, if you want to determine the complete set of view factor, you need to know precise, you basically need to know them a priori, is what this view factor matrix and this and this argument uh, which we have put forward suggests us. Okay, now I hope this thing is clear, and this is one of the most, I would say, important aspect into knowing that how much view factor you need to know beforehand, and how much view factor are the relations that you have basically can give you. Okay, uh, into extending the analogy for any generic n surfaces. I hope this is clear to you until this point, or up to this point. All right, so this ends the discussion on view factor. We have done an extensive and a thorough discussion involving view factor, and if you are clear up to this point, you can trust me, you can solve any problems involving view factor analysis. You just need to know the generic definition of view factors, that is the integral uh, formulation that we have said, the view factor reciprocity relation, the view factor summation rule, and the idea that how many view factor you can get from a generic n surfaces, and how many view factors are obtained from the summation rule, from the reciprocity relation, and how many view factors should be directly given to you, or at least you need to figure them out by using the geometry, by using symmetry argument, by using inspection and things like that, typically. Okay, so with this, we will start off now with a new topic, which is the radiation exchange between um, black bodies. But before that, I'll stop here for a couple of minutes, and I'll let you guys to absorb whatever we have discussed until this point. Okay, let's get started. So So what I mean by trying to understand radiation exchange between black bodies is that, let's say I'm considering a generic body AI, and I'm assuming that AI is a black body, and I'm assuming another body which is AJ, and so is AJ a black body. So AJ is also a black body. Then I can now say that, so I can now define a quantity Q going from I to J is, so Q going from I to J is the radiation that leaves surface I, which is a black body, which is intercepted by surface J, as the area of surface I times the radiosity of surface I times Fij, which is the view factor Fij. And that's how now the view factor essentially come into the picture of solving realistic problems involving radiation exchange. Okay, so Qi to j is nothing but the fraction of radiation that goes from surface I, which is intercepted by surface j, which is nothing but the area times the radiosity times Fij, which is nothing but the view factor Fij typically. Which is, so Fij again is nothing but the fraction of radiation leaving surface I that is intercepted by surface j, or in other words, the view factor Fij. And similarly, I can also define Fji as the fraction of radiation, or it's not the I mean, Fji is nothing but the radiation that leaves surface j, which is intercepted by surface I, as aj times jj times fji. Okay, but since ai and aj are black surfaces, I can say that Ji, which is the radiosity, is equal to Ebi, which is the emissive power for the surface I, and Jj is nothing but equal to Ebj. So I can now write this as Ai times of Ebi times Fij, and this is nothing but Aj times Ebj times Fji. But since we are interested in the net radiation exchange, so I can now define the net radiation exchange, which I will define it as Qij, and this is going to be the difference between Qi to j minus Qj to I, and that's how the net radiation exchange is essentially defined. And I can then write this Qij. So Qi to j is nothing but Ai times Ebi times Fij minus Aj Ebj times Fji. So this precisely gives you the net radiation exchange taking place from body I to j typically. Okay, now, but I know that from the reciprocity relation, Ai Fij is equal to Aj Fji. So if I substitute 2 in 1, I can then say that the net radiation exchange precisely becomes equal to Ai Fij times Ebi minus Ebj. And from the Stephen-Boltzmann law, I can then say that Ebi is nothing but sigma times of Ti raised to the power 4. Okay. And similarly, Ebj is nothing but sigma times of Tj raised to the power 4, which means the net radiation exchange between any two generic black bodies can be written as Ai Fij times sigma times Ti raised to the power 4 minus Tj raised to the power 4. Okay. And what you can do is you can similarly write this by making some rearrangement as sigma times Ti raised to the power 4 minus Tj raised to the power 4 by 1 by Ai Fij, and this can be equivalently written as Ebi minus Ebj by 1 by Ai Fij. So remember, in conduction heat transfer, where we have said that the flux is equal to T1 minus T2 divided by resistance, we have equivalently formed a similar analogy for radiation as well, where now instead of the temperature difference, we have the emissivity difference between the two bodies, or in fact the emissive power difference between the two bodies, and this Ai and this 1 by Ai Fij, this can be equivalently written in the form of a resistance, and we call this as the space resistance. And then you can now form a resistance network between the two nodes. Now there will be this emissive power nodes, which will be Ebi, and this will be Ebj, and this resistance is nothing but 1 by Ai Fij. So equivalently, you can write the net radiation exchange in the form of a resistance network for black bodies at least. And now you have these two emissive power nodes, and the resistance is 1 by Fij, and this resistance, as I said, this is known as the space resistance because it arises basically due to the space. So the important thing you need to appreciate that now you cannot have these temperature nodes because your temperature actually comes in the fourth power. Instead, you are defining the nodes as an emissive power nodes, okay, where the resistance is just 1 by Ai Fij, and this is the resist. So this is typically the resistance network to evaluate the net radiation exchange between black bodies. Okay, so that's how you essentially, so this is a formal way of defining the radiation exchange taking place, between black bodies. And trust me, for real surfaces also, you can equivalently define a resistance network where now we will encounter extra resistances, which we will call it as the surface resistances. We'll not discuss the details, so that is something that we'll do, you know, thoroughly in the next discussion hours. But just to give you a heads up, this is also something that is possible for real surfaces as well. But at least for black bodies, this is how you define the net radiation exchange between two black bodies, written in terms of, either you can write this in terms of the emissivity or emissive power, or you can write this in terms of the temperature, and you can equivalently define a space resistance associated with this, and this will give you the resistance network for evaluating the net radiation exchange between black bodies. Okay, so going forward in the next class, we will try to understand radiation exchange between real bodies, and we will form something, and we will form an equivalent resistance network for real surfaces as well. And as I said, we'll encounter one more type of resistance, which is known as the surface resistance, and we will see how it turns out to be. And towards the end of that, we will learn something which is known as radiation seals, where and the practical application where these resistance network come into the picture in radiation heat transfer is trying to understand heat transfer taking place in these radiation seals. uh, and this is something that we will see extensively in the next discussion hours. But we will end the discussion for this session by until this point, where we have tried to establish a radiation network involving the radiation exchange in case of black bodies typically. So just to give you a recap, what we saw is we started off by trying to understand the definition of view factor, okay, where we define the term Fij, and then the mathematical form of this Fij, although we didn't derive this because this derivation is something that you have already witnessed it in the week's lecture series. So just for repetitiveness, I have not shown this derivation, but as I said, the idea of the derivation comes from the definition of intensity of radiation, and then assuming the fact that your surface is a diffuse surface, from which you can define this view factor Fij. And similarly, you can define the view factor Fji, use the fact that the integrand is just the same, which gave birth to the reciprocity relation, and then we kind of develop the summation rule, which looks something like this, and then solve the numerical, where you have used the generic definition of Fij to actually calculate what this Fij turn out to be, where we saw a disk of a finite area and a differential area of AI or some dAI, where AI was much later than AJ, and then calculated the view factor Fij in terms of the diameter of the disk and the distance between the center of the disk and AI. And then we looked into the other aspect of solving view factor problems, where we use the reciprocity relation and the summation rule. And then we generalized the fact that if I have an enclosure of n surfaces, how many view factors do we need how many possible view factors can arise, how many view factors can come from the relations, for instance, the reciprocity relation and the summation rule, and how many view factors can be obtained directly, or how many view factors are needed to be known directly. Okay, and thereafter we form something which is known as the view factor matrix, which stores the entire information of the individual view factors that can be possible for any generic n surface. And we also saw the individual cases of a two surface and a three surface scenario, and form the view factor matrix for these surfaces. And then we ended our discussion by trying to understand radiation exchange between black bodies. And equivalently, we said that we can form an equivalent radiation network analogous to the radiation network that we define in case of conduction heat transfer, and also convection heat transfer, where we saw that now the nodes become precisely the emissive power nodes, and the resistance that come is in the form of a space resistance of the form 1 by AI Fij. And you can also similarly write this resistance as 1 by AJ Fji, that is typically because of the view factor reciprocity relation. Okay, so this ends the discussion of this this discussion hour. I hope you enjoyed watching this. If there are any questions, as I say, please feel free to post it in the discussion. I mean, in the discussion forum of the course, and do let me know if there are any doubts that are that may arise from this. And also, if there are any doubts related to the assignment, please feel free to post it in the discussion session, as I always say. and and going forward, as I said, we will be learning to draw the resistance network for radiation, for estimating radiation exchange between real surfaces. And this is the idea that we will try to explore it in the next discussion hour. And I thank everyone for watching these videos. We'll meet at the same time in the using the same link from 3 to 5 next week, and maybe we'll have two more sessions, uh, and then we'll end the discussion session, and thereafter we'll have your exam week for this course. Okay, thank you very much, guys, for watching these videos. We'll meet next week.